So I'd like to segue, and I challenge you to spell that word correctly, to our guest speaker tonight. And I want to introduce to you Dr. Philip, otherwise known as Phil, J. Erickson, with a vanity call sign of W1PJE.
Guilty as charged.
So he has in parentheses extra class. He is head of the Atmospheric and Geospace Sciences Group, a principal research scientist and an assistant director at Haystack Observatory, operated by the Massachusetts Institute of Technology, otherwise known as by the three-letter abbreviation of MIT. Yes. He is a member of the ARRL, RSGB, TAPR, and the Nashua Valley Amateur Radio Club and the HAMSI Initiative. Phil is the lead principal investigator of a National Science Foundation-sponsored UHF megawatt class ionospheric radar at MIT Haystack. So there. He's got more megawatts per hair follicle than the rest of us. And some of us are really hair follicle challenged. Operating since 1960 for community studies of the near-Earth space environment, he has authored or co-authored 80-plus peer-refereed articles in the area of ionospheric and magnetospheric phenomenon and radiophysics. Phil holds a Bachelor of Science and a PhD degrees in electrical engineering and space plasma physics from Cornell University, and is a member of both the American Geophysical Union and the International Radio Science Union. He started his radio career, as many of us do as shortwave listeners, with a random wire and a Holocrafters SX110 receiver, and enjoys radio in all forms, amateur and professional, 6-meter and HF, QRP, EME, RF design, and digital weak signal modes. And when he's away from the radio waves, Phil chases his miniature schnauzer around the house and enjoys music and kayaking with his wife and middle school son. I give you Dr. Phil Erickson.
Thank you very much. So thank you to Steve, thank you to the whole TAPR board, and thank all of you for being here tonight. I have to say this is my first TAPR meeting. I definitely need to come back. I've had a really, really enjoyable time here. The technical level of this conference is right up there with all the other professional meetings I go to, and in some cases, you guys get a lot more done than the people that I sometimes hang out with that argue about this part of physics and that part of physics. So it's nice to be around a bunch of implementers, all right? And I think that between what I'm going to say tonight and what Nathaniel is going to lead tomorrow morning, which I all encourage you to come to that session, I think we really have an opportunity to do something quite special in this community. And it's quite clear to me from all of the talks that were given to the nice history that Steve gave, and even I didn't know half of that stuff that had been done quite a long time ago. This is where the innovation happens. And I hope to be able to show you tonight that I really think there's a great connection we can make. And frankly, both the amateur community and the professional community are ready for it. So I think the time is right. You know, this is the title of what I'm going to say tonight. Hopefully a few interesting things sprinkled in here and maybe some things to think about. I want to point out this particular thing right over here. This is the cover of the Westinghouse Engineer from late fall 1946. That is one of the first places that the magnetron was put out in the public domain. The magnetron, as you know, was developed by many people, including the MIT Radiation Laboratory in World War II, but the device was, of course, restricted to military applications, and this was one of the first times that it had appeared and made certain microwave generation possible, not only for amateur purposes, but also, of course, for commercial electronics. And at least still today, there's one of these in your microwave oven at home. So I put this here as an indication that there are things that can emerge from technical communities or sometimes from commercial applications that immediately have an impact on what we can do in the academic research environment. So who am I and why am I here? Whoops. Wow. I've lost my voice. Okay, here we go. Anybody remember Admiral Stockdale? Who am I? Why am I here? Some of you do. Okay, so Steve mentioned the Hallicrafters SX110 there, and for those of you who are Valve fans, there's the lineup of what was in that radio. This is what I started with when I was about my son's age. This is, on my mother's side, this is a family business that's been running, it'll be 100 years next year. And the building, I used to go and visit my grandparents on the weekend, maybe once a month or something like that. I come from Schenectady, New York, so upstate New York, and this is in Dutchess County, so it's not too far, it's an hour and something drive. And in the bedroom right up here is where I used to stay, and so somehow my uncle, who runs this store and would get things in trade for various things, ended up with that. And so in this bedroom, I used to listen to things late at night, but I needed a random long wire, and so do not tell my grandmother, but I climbed out on this hip roof and ran the wire off that way. That building was constructed in 1865, and I'm terrified that I did that. When I look at the building now. But I used to sit there, and I got a thrill tuning into Voice of America because, of course, as a US citizen, I was not allowed to know what the schedule was in Voice of America because that would have been propaganda. But I could at least hear what VOA was telling the rest of the world. And I put this up here because my favorite was that there was Vatican Radio. And they would, for 15 minutes a day, give the news in English. And it was this woman who sounded like she was about 140 and would read the news in this very quavery voice, and in a sharp Italian accent, she would say, "Good evening from Rome, Italy." And then the bumper music would come on, and then they'd go to French or German or Spanish. And I thought this was absolutely fabulous. I mean, I had this roll of wire that I had gotten at the hardware store up the street. So I was hooked, and I don't think that's a stretch to imagine that everybody in here has a similar sort of tale, that how they got interested in radio. It turns out I had a family history. This is my uncle back in 1957 hanging out with two of the telegraphers down at the New York Central Railway agent. And so he actually picked up Morse from them, and as they were sitting there, of course, transmitting traffic, usually telegrams, some of which were taken by my mother and pasted up on little Western Union form. She hated the ones that she had to do the singing telegrams, not her favorite. But he picked up Morse from them. He still has the Morse key sitting there in the store and uses it occasionally. So CW was even running somewhere in my blood. I unfortunately did not pick up the skill of these guys quite yet, but I'm working on it. So then I ended up going to Cornell for undergraduate, and they had a nice co-op program, and I actually spent a couple of summers at the General Electric Research Laboratory, which, being from Schenectady, was kind of like being home for the summer, which is one of the great industrial research laboratories, along with the things like Sarnoff and IBM and other things that I'm very privileged to be among alumni in this audience, frankly. I'm very honored, actually, for that. And one of the people that worked at GE was, in fact, Irving Langmuir, the guy who coined the word plasma in the 1920s. He was a physical chemist, Nobel Prize, and he discovered a very fundamental oscillation that actually occurs in the upper atmosphere. That's a microwave tube, and they were trying to increase the efficiency of the tube in 1920, and there was this funny high-pitched buzzing that they couldn't get rid of, and they gave him the engineering problem to fix it. Being a physical chemist, he said, you know, there's probably something going on there, and in fact, he discovered there was a plasma in the tube, and it was oscillating. It's a little hard to read this quote, but when he arrived at the laboratory, the director told him to look around and see if there's anything he would like to play with. The director would ask him, "Are you having any fun today?" One day, after 3 years of apparently unproductive research, he said, "I'm having a lot of fun, but I don't know what good that is to the GE company." And Whitney said, "That's not your worry, that's mine, go back to the bench." Very seriously, we have lost a good amount by not running industrial research laboratories as basic physics, chemistry, and biological generation things where you're doing basic research and then you worry about patenting things afterwards. Not everything is an applied research problem. And Langmuir is a classic example of that. So I even got to Langmuir's lab assistant lived down the street from me when I was growing up, so I'm very proud of that, too. And somebody pulled up old web pages. This is from the Internet Archive. I arrived at Haystack after completing graduate school in 1995, and unfortunately the Internet Archive does not go back that far enough. It starts in 1997. This was a web page that I wrote in Mosaic. Somebody mentioned Mosaic earlier. Haystack was on the web in 1993, thanks to one of our visionary scientists who realized that maybe there was something to this. And I don't look like that anymore. So very gradually, I got immersed in not only radio physics, but also in looking at the upper atmosphere, and in fact, the near the space environment. And this is where I am right now. This is the MIT Haystack Observatory complex. This is on a little hill in Westford, Massachusetts, so that's about 50 kilometers northwest of Boston, along Route 495. In the 1950s, when Haystack was put together, this was frankly, there was no 495. Route 128 had just been built a few years before that, and 495 was 20 years in the future. This is where people went to spend their summers, little summer cottages, believe it or not. That was their summer home out of Boston. Doesn't look like that anymore. We're hemmed in on all sides. But this site developed actually as an outgrowth of other technology. This was where the prototyping for the ballistic missile early warning system occurred in the 1950s. Lincoln was given the task of detecting something at a much farther range than normal, basically something coming out of the atmosphere and coming back down. And they wanted a place where they could have enough buffer land that they could do large transmitters and large antennas, and then the site gradually grew from there. So Herb Weiss, who put the site together, wanted to get 5 square miles. He got 3.5. So we have about 1,300 acres. And no horizon blockage. The first set of mountains for us is the White Mountains that way. This way. So we have a really tremendous field of view. So we developed programs in radio astronomy, so don't transmit, but listen. Atmospheric science, in our case we run radars, so we transmit as well as receive. The site is shared with Lincoln Laboratory, which is where it started, and there's an enormous space surveillance program looking at updating orbital elements for orbiting objects, imaging them. That's a 37-meter antenna that actually does imaging up at W band, 95 gigahertz. And we're all doing radio science in one form or another, except for that thing. It is an electromagnetic wave, but it's just such a short wave. And I do a lot of education and public outreach. So I'm now leading some programs that actually will deal with this particular system, and I'll tell you more about that in a little bit. But obviously, we deal with large antennas, really sensitive ones, and reasonably loud transmitters. But it's a transmitter and a receiver and a transducer to get the radio waves out into the environment and back, and you're all familiar with that. So let's back up a little bit. I think my motivation tonight is to show you that our upper atmosphere, and in fact the whole atmosphere, is many, many orders of magnitude from being a solved problem. And in fact, there are many, many variations in this environment that we honestly don't know that much about yet. And I can guarantee you that the signals that sometimes appear in your receivers when you turn them on are related to things that I think we can learn about together. But we need to set the stage. So, I referred to this when I was giving the eclipse talk with Nathaniel a little bit earlier, is that, we have this sun, okay, nearest star, and it emits a lot of radiation, and there's some of it at extreme ultraviolet. So in case you can't see this, this is essentially the spectral irradiance that's coming off the sun kind of on a typical day. This is the far infrared here. This is the near infrared, this is the visible, this is the near ultraviolet, and this is the extreme ultraviolet. And this is a log scale. This is a radiance in milliwatts per meter squared per nanometer, so there's a normalization of frequency. And this is what a 10,000 degree black body would look like. Okay, so that's why you'll hear sometimes the sun kind of appears like a black body in terms of its radiation. And here we are seeing each other with the visible, and you'll notice that the output is quite a bit larger in terms of complete irradiance here compared to here. There's a lot of choppiness here. The bottom is the variability in percent for that same wavelength range. Notice that the optical is down here at 1/10 of a percent variability. And that's why I mentioned yesterday, you don't go out in outside and say, Mom, it's solar minimum, I need a flashlight, right? This is fairly constant in output. You can also speculate that maybe we evolved to have an electromagnetic sensor that was in a place where the illumination was actually fairly stable. But these have got a lot of punch, and the extreme ultraviolet photons have enough energy that they can rip electrons off of neutrals. And look at the variability. That's 100%, that's 1,000%. So honestly, this stuff is moving all over the place. And there are patterns from milliseconds to millennia that are part of this variability. That's why the local environment is so interesting. It all starts with the sun. I put this up before. The idea is that, again, the neutral atmosphere is gradually absorbing all that EUV, creating these particular layers, the E layer, the F layer, even the D region where things are highly collisional. By the way, the E region that we all know about through things like sporadic E is a very special place. It actually, of course, goes away fairly fast, maybe within an hour after sunset. It's pretty much gone down to the point where I have a hard time detecting it. And it's a very special place. Right there, the electrons are still really magnetized and stuck to the field lines. But the ions, being a lot bigger, are actually now collisional. And they start getting bashed around by the neutral atmosphere. So in a little thin layer right here, you've got the pluses getting moved off by collisions, but the negatives are staying over here. What does that sound like? That sounds like an electric field, right? So there's an electrojet flowing at that altitude because of that property. Above here, it's not collisional enough, and in fact, both the electrons and the ions kind of move together and can get pushed along the magnetic field line. And below that, everything's collisional, and you start not to really worry about where the magnetic field is. So this is a very special place. And it changes from day to night, as I mentioned, and the fact that the E layer goes away, but the F layer remains at night is one of the reasons why long skip propagation, of course, changes from day to night, and when the sun comes up and the sun goes down. And so even in terms of a climatology or a background, this is very interesting and very variable. I showed this before. I just like that, it's 24 hours in the life of the ionosphere. And this is derived from GNSS signals, as I mentioned yesterday. The same things that you have to take the ionosphere out of your navigation signals because they would cause an extra delay, which is going to screw up your navigation calculation. But if you save that delay, you get space weather. This is I took this as August 21st. So this is, 3 weeks ago. KP was 1. Things were fairly quiet. I would venture to say that is not at all uniform and just falling off nicely with the equator. There's a lot of structure even in a quiet day. So again, this is space weather. And this is something that, frankly, our community is just getting to. We are getting to understand maybe some of the background climatology, but now we have to look at the variability around that. So Bob mentioned ionosons, okay? One of the oldest techniques for actually sensing just the electron density profile, you send a wave up, and when it gets to the point where it's actually matching the local plasma frequency, that frequency that Langmuir looked at way back in the 1920s, which to zeroth order is, I've got a box of plasma, and I'm going to take all the electrons, and I'm going to move them over here. I'm going to leave the ions behind, I'm going to let go. Okay, the pluses and the minuses want to come back to others, so they do that, and then they overshoot, and then the force reverses, and they slosh back and forth, and that's the plasma frequency. And that's a very strong function of the electron density. It's actually, the frequency goes as the square root of the electron density. So, as Bob mentioned, if you transmit a wave, at some point it will reflect, and if you measure that delay, you can actually measure the height to that particular electron density, and you can sense part of the profile. Only the bottom, because you can't see the top, it's sort of shielded from you. This is from Terry Bullitt, who has done a lot of things for NOAA, and I just thought I'd show you that this is, for example, one trace from an ionosonde, and in fact it's polarized, and this is the ordinary mode, and this is the extraordinary mode. So the extraordinary mode comes back at a little bit different than the ordinary mode, so in fact it's polarized with respect to the magnetic field. Here's a day in the life of the ionosphere. So here we are somewhere in noon or early afternoon. Notice the double hops here. And as we get toward night, because now the frequency is dropping, watch these lines, and you will notice that they no longer become single. They're going to start spreading out. See right there? That's irregularities in the electron density. So you're getting echoes at a range of frequencies, not just one, in the middle of the night. And so here it is, hopping along. You'll notice the double hops that everybody likes to use for long skip are coming and going here. And sunrise will be reasonably obvious when it happens here. So look, now we've got two different traces. So we've got within the ionoson's beam, we've actually got two different frequencies. So we've got some plasma at one electron density and some plasma at another electron density. And at some point here, let's see, boulders, 13 UTC. Here comes sunrise. Notice all the structuring. And this is just an ionoson, folks. This is just measuring the electron density profile. Lots of natural complexity, variability, space weather. And if you don't transmit your beam straight up, but you transmit it on a slant, so now I'm going to kind of reflect off the bottom of the ionosphere, and I'm going to come back, so my transmitter is here, and I'm going to receive something over here. It gets even more interesting. Notice how many hops. 1, 2, 3, 4, 5. This is range in kilometers. That's 3,000 kilometers. Anybody notice that your maximum usable frequency, MUF, is calibrated to a path length 3,000 kilometers long? That's about the top of this graph. Look at all this structure. By the way, there's something else very interesting in this. First of all, this is at HF frequencies. There's 40 meters. There's 80 meters. There is 20 meters. See all of this stuff right there? That's C-scatter. You're actually getting ocean wave information out of that same data set. And it's just happening, yes. And in fact, there are people who are building sensing systems that are going to look at ocean height from looking at that scatter. There's people at the Superdarn group, in fact, in Virginia Tech. I bow to Bob McGuire.
They're going to use the red battalion.
That's right, as Bob mentioned. So there it is. Even more interesting. This is a simplified chart. This has only got some of the processes on it. Hopefully you're all good eyesight and can see all of that. This is honestly just a sketch of all of the processes that are going on in the coupled upper atmosphere and lower atmosphere. My colleagues at places like NCAR are now simulating the whole atmosphere. They're starting at the ground. Right now they're going up to 500 kilometers. Their job is to get out to an Earth radii. Because all of these things are all coupled to one another, and as you can see, it's different at the equator, at mid-latitudes, at high latitudes where the aurora is. The ionosphere, the ion part and the neutral part are all intimately coupled, so one moves and the other one tries to move along. And then in high latitude, you get direct entry into the upper atmosphere for things like high-energy charged particles from solar wind events. Our magnetosphere fortunately shields us from that down here, because life would be kind of bad if I was constantly getting irradiated by MeV-class particles, but we have a magnetosphere, which is very nice. I appreciate the magnetosphere every time I look at this graph. So, all of these things happen. The plasma can go unstable and emit its own waves. The plasma can structure. It can move from here to there. It can move in 3 dimensions, in altitude as well as horizontally, and it changes with respect to time. And these have direct effects in the radio propagation that we all enjoy or curse, depending on what day we're trying to use a particular band. But this is fundamentally a radio science audience. So I want to point out to you that one of my professors at Cornell, Mike Kelly, who unfortunately just passed away a few months ago, pointed out that this is actually an EE problem. You can actually model the upper atmosphere as a circuit. You have a charged plasma moving, which has got charges in it, in the solar wind. And what is it doing? It's moving across the top of the planet, and you have a magnetic field. If you pass current against a magnetic field, what are you doing? It's a generator. You're generating a potential drop between here and there, which, by the way, is quite a number of kilovolts. That actually maps right down, just like wires, into the high latitude ionosphere, where it drives a current. Think about a resistor down in here. And that current actually causes things to move and also gets the particles accelerated down the field lines where they crash into the atmosphere and cause the aurora. But you can think of this as a circuit. Not only can you think of it as a circuit and apply Ohm's law and Kirchhoff's law and all those other things that you learned in your undergraduate radio science or EE class, but you also realize, well, then you can, for example, Nathaniel back there spent a good amount of time looking at convection cells using HF radar, same frequencies that we've been talking about, and scattering off irregularities, and if this were a movie, you would actually see these cells move. They're moving like this because there's a potential drop from here to there. There's the plus, there's the minus, and it's being driven by the solar wind. So if you know about generators and you know about motors, that's what drives this. So there's a direct electrodynamic feature to the ionosphere because it's charged. Part of it is charged. And it's not local, but it's global. Why? Because these field lines are like wires. The electrons really want to go along the field lines, so they have very, very low potential drops. So you can model it as a circuit where you actually have a northern hemisphere E region, a southern hemisphere E region, where there are some currents that are generating and there are things that are dissipating. And same thing that you can actually have some of that happening up in the F region. There's a potential drop between these two. So both ends of the magnetic field line matter, which means that this is a non-local problem. What happens when I'm home and I'm at Millstone Hill in eastern Massachusetts, fluctuations up there are electrodynamically coupled to a location that's off the tip of South America, just above what used to be called the Palmer Peninsula. If there's a Russian station called Vernadsky Station, if you actually look to the west of that, and you took that place, it's magnetically connected to Massachusetts. So one of the things we do in research is we actually look for signatures in one hemisphere and signatures in the other, and many times they're exactly coupled. So it's a challenge. It means I got to measure everything everywhere, which I will get to. My colleagues also push this farther and actually have put together the global electric circuit. Lightning, which is dumping a lot of charge from here to there, circulates charges up into the middle atmosphere through things like something called the Wilson storm current. These are charges that are riding along on top of neutral molecules, coupled up into the ionosphere thermosphere because the ionosphere is charged, and then up over those field lines, and there are numerical models that are attempting to model all of those fluctuations as an electrodynamic problem. And we know about radio waves here, so we know about electrodynamics because we rely on those to launch waves. So this is at the forefront of where we are in the field. This is not something that's in a textbook that was written in the 1950s, and we're done. And notice the complication is that where does the field point? It points different places in different spots. If you're at the equator, it points straight overhead. If you're here at mid-latitudes, it's tilted. If you're up at the high latitudes, it's nearly vertical. So the direction that it's easiest for the electrons to flow in is constantly changing depending on where you are. So that makes it even more interesting. Most people have heard of the word space weather because this is where the basic physics kind of meets the fact that we have an increasingly spacefaring technological society, and our complexities of technical systems certainly have been increasing a lot. This is Lou Lanzarotti at NJIT, who some of you may know, who has been doing space weather for a long, long time, back to Bell Labs when he was doing stuff that I'll show you in a minute. Yeah. Somebody mentioned Telstar, I'll get there. But we can go back to the 1840s to look at the first sort of indications of space weather when this was the technical system that we had. This is a guy named Barlow publishing in 1849. This is a galvanometer, think of it as a voltmeter, as in a 24-hour period in 1847, and suddenly there was all of these swings on these very long telegraph lines in England. This is from Derby to Birmingham, two cities in England. And notice, in every case which has come under my observation, the telegraph needles have deflected whenever Aurora has been visible. He was basically seeing electrodynamic coupling from all of those currents flowing overhead, coupling into these long wires. One of the earliest indications of space weather affecting a technological system. And then there's the Carrington Event, which has worried people ever since it happened. This is the largest geomagnetic disturbance for the last 500 years. We may get another one tomorrow, we don't know. But in this case, this was strong enough that this guy named Carrington, and by the way, solar rotations are counted in Carrington rotations now, which will tell you how important this was. He was sitting there looking at sunspots, which people did to try to understand what the sun's output was, and they were being projected on a piece of glass, and he would have a piece of tracing paper and count the sunspots. And there was a very rare white light flare. It's a sunspot that actually is in white light rather than being dark. And it was so bright that he figured something had shattered the glass and that the sun was actually coming through the glass, because he couldn't believe that this thing was that bright. At that point, magnetometers and Greenwich shingling went off scale. This, again, was the largest. You guys have seen geomagnetic storms at solar minimum or solar maximum. This was intense enough. That's where the aurora was seen at that time. Aurora in South America, all the way down to the magnetic equator. This is what people worry about in terms of the extreme space weather event. When will the sun throw another one of these out? We don't just have telegraph lines. Now, and there's a nice anecdote that even goes along with this. There was two telegraphers working the line from Boston to Portland on September 2nd, 1859, and they got to work their telegraph keys for 90 minutes with no batteries, with a voltage that was being intercepted by the fact they had a long piece of wire with a voltage drop across it. Some of the telegraph lines, actually the poles caught fire, a couple of the telegraph stations burned down, a couple of people unfortunately were killed, I believe, in the fire, because there was the ohmic heating, right? Drive kiloamps and megaamps through these things. But if you know New Englanders, this was the operator exchange. My battery's disconnected. How are you receiving it? Better with the batteries on. Shall we get on with it? And they sat there for 90 minutes, and one of them said, Fred, we should put the batteries back on. And they just continued. And that's, somebody called the Times and said, something funny happened to us. So this is an extremely intense space weather event. Imagine now if we had this happen. Imagine how many things are in orbit. Lou Lanzarote worked on Atlantic telegraph cables at the time, another long piece of wire. They looked like this. This is the one coming up from Trinity Bay out of the ocean into a telegraph site. Apparently, if you go to Newfoundland, this is a historic site. You can go visit it. One of the terminals of the transatlantic cables. There's even a book, and the beginning of cable service was far from reliable. Earth's magnetic currents, lightning the Aurora sent the galvanometer to wild and rapid gyrations. So in addition for dealing with transcontinental cables, they had to deal with all of these huge voltages that would sometimes appear. Again, a space weather effect on the technological system. Back in 1940, a nice magnetic storm. Look at all of these problems, all of these electric grids in Maine, Massachusetts, Minnesota. Transformers started tripping off, 220 kilovolt transformers. And this was the potential between Minneapolis and Fargo on March 24th, 1940. That's volts. So there was like a 300 or 400 volt drop in between this relatively short long line. The first major industrial conference happened at that point because they said, geez, we better try to understand what was going on. And that obviously affected these nice telephone lines everywhere. And so gradually things began to be studied. There was another one in 1958. Anybody know what the International Geophysical Year was? 1957, right? So this is the year after that. This is the first transatlantic telephone cable coming into Scotland. That's kilovolts. So there's a spike of about 1.5 kilovolts on the cable under the North Atlantic. So penetrating all the way down to the bottom of the ocean, and circuit breakers tripped out and the Toronto area went offline for a while, broken only by the strange light of the aurora overhead. We don't get people who write like this anymore, but they did at the time. So again, space weather effect on a system. And then there's man-made space weather. So who mentioned Telstar 1? Somebody did, right? Okay. We know who this is. This is James Van Allen, who serendipitously discovered the inner and outer radiation belts that are surrounding our planet, naturally trapped radiation with a little gap between them. I get to work with instruments on something called Van Allen probes, which has been going in and out of the radiation belts for the last 7 or 8 years. This is totally a wrong picture, by the way. just so that you know. These belts, by the way, when people first discovered them, nobody knew if they were naturally caused or if they were the result of above-ground nuclear tests. And so a guy named Nick Christopoulos figured out that energetics meant that these had to be generated naturally, scooped up particles from the solar wind, in fact. And this was discovered by Explorer 1, if anybody knows about Explorer 1. The only scientific instrument was a Geiger counter, pretty much. And the Geiger counter went through the belt, and the data went up and up and up and up, and then went to 0 for a while, and everybody said, Van Allen, your probe broke. There was actually so much radiation that it ionized all the gas in the tube, and the Geiger tube stopped counting. And then when they came back out and enough electrons had recombined, the counter jumped up back again. He had discovered the belts. His colleague, whose last name I can't remember, the first name was George, left a note in his door, his chair the next day that said, "Space is radioactive," with 3 exclamation points. They thought that was the end of the manned space program. You know, you're going to kill anybody who goes through the belt. Turns out if you go this way, you're okay. Why am I putting this up here? Because we were still doing above-ground nuclear tests. This is the Starfish Prime test. This was a nuclear weapon at 400 kilometers altitude. That's artificial Aurora over the Pacific. It blew out half the Hawaii telephone system, and it created an artificial radiation belt that lasted for quite a while and took out probably half of the orbiting satellites in the 1960s, but there weren't that many, including poor Telstar 1. Look when it was launched, 10 July. The test was 9 July. It died from radiation damage in early February. Man-made space weather happens too. Fortunately, we don't do these tests anymore. At least, according to international agreement, we don't do these tests anymore, and there are people who worry about that. But even in space now, space weather can have a large effect. And then there's the economics of space weather. And before the last thing I'll say about it is that space weather has been studied as something that hits people in their wallet. So in fact, there are studies that say essentially there's a spot price for power. Companies buy and sell power just like they as to set their price per kilowatt hour. And if the grid starts going nuts in Canada, as it did in March 1989, because there's a lot of voltage, New England disconnected itself from the rest of the grid to protect its generators. And that meant that they had to buy the power from somebody else because the factories were still online, and the price of the spot power went way up, and it hit them right where they live in the wallet. So honestly, this argument makes them sit up and take notice. It's an economic argument. It actually affects the spot price of normal electric power. So there's a couple of nice studies in Space Weather Journal about that. And by the way, congestion loss due to these particular things, $1 billion in the first 6 months of 2015, where they had to disconnect occasionally due to unsustainable currents flowing. These are huge numbers. So even industrially, people are interested on this. And I'm leaving out the fact that you may burn out a 500 kilovolt transformer, excuse me, if you flow too much DC current through it. So how do we study this environment, okay, if it's really got all these dynamics? I put an O after QRO for every factor of 10 above a kilowatt. I added in the antenna gain. These are probably not found in your basement. Why am I saying this? Not to show you that my car is bigger than yours, but honestly to say that this is an example of what one does for research grade stuff, but I want to emphasize it's not the only way we can figure out this environment. It just happens to be a way that the science community is used to doing this. So what do I mean by that? Well, this is called the Millstone Hill Incoherent Scatter Radar System. Here we are in Massachusetts. This is our field of coverage at 500 kilometers altitude, because we're up on a hill, so we cover most of the eastern US. You'll notice the numbers here. My transmitter generates about 2.5 megawatts at 440 megahertz. We operate this about 1,000 hours a year, a little more, and we're operated, this is a facility that that are operated on behalf of the National Science Foundation for the research community. So we are an observatory, so we make measurements and calibrate them and provide them to scientists. We've been doing this for over 50 years now. This is the field of view of our instrument looking from north to south. You notice the large range of just electron density structures we went through here, or we can measure vertically. These are my antennas. That's a truck. And what we're looking at is fundamental scatter from the free electrons in the upper atmosphere, which are pretty tiny. I mean, statistically, a little electron is about 10 to the minus 14th meters diameter, or 10 femtometers if you work it out. That's what Thomson did in 1906 when he posited there must be an electron. So even a large box of electrons, like it's in the upper atmosphere, doesn't give you too much scatter. But it turns out that if you very carefully measure this, and I thought that the coding talk by Michelle was quite interesting, because normally you have Gaussian noise in your system that you don't want, and then you have some other kind of coherent signal that you want. I have a very different job. This scatter from the electrons is also random. It just has a different spectral shape. So I'm actually trying to take one noise process and subtract it and reveal another noise process. But if you do it right with signal processing that frankly would be familiar to some of you, you can get these little double humped shapes, and if you plug in a first principles plasma theory, you can figure out not only the electron density, but also the electron temperature, the ion composition, the Doppler shift by watching this move back and forth, and that plasma line, which was discovered by that guy Langmuir that, whose assistant lived down the street from me. And so we send a 2 megawatt wave out and we get back 20 femtowatts, even with a collecting area that big. But it's above the noise floor. So in the 1950s, people figured out that this could be measured. And there's only about 12 of these radars in the world, at least yet, because the power levels and the apertures are a little big. So I figured I'd show you a little bit of what would happen if you guys were coming for a tour. This is my 150-foot or 446-meter fully steerable antenna that has 42 dB one-way gain. Anybody work 70 centimeters here? Yes. There you go. We have listened to the moon for EME. I wish I had time. I have a recording of somebody that's S5, a Swedish amateur who was transmitting SSB off the moon with no other processing gain, and we could hear him quite clearly. But why do I have these things? Again, not to brag, but this is the size of antenna you need to look at this really weak scatter. And the happy accident for physics is that the size of system you need to detect a ballistic missile at about 3,000 kilometers altitude is exactly the same size to do this work. This is all military surplus. Your taxpayer dollars at work. So this is 150 foot or 46 meters steerable. This one is older. This is 220 feet or 68 meters. That's got 45 dB one-way gain, but it only points up. And so we can switch back and forth in about a second between this one and this one, because this is a slow, clunky mount and only moves a degree per second, so it's not going to be tracking a lot of satellites, but it's fine for doing ionospheric work. These are my transmitters. This is surplus from the ballistic missile early warning system. They have to live in a lead-lined cabinet because they spray X-rays all over the place up here when you run them. I'll show you a couple of the parts here. These were taken out of working ballistic missile part systems most up to about the late 1990s. Unfortunately, we're having to move off this to phased array technology because these tubes are not made anymore. They were made by the Litton Corporation, which was competed with Varian, for example, for doing Klystrons. This is the Klystron. It's a 4-cavity tuned microwave amplifier. And it fits in a coil jacket. So remember vacuum tubes? There's a filament down in here. Heat the filament, electrons boil off into a beam. They enter an evacuated chamber, and they start encountering tuned cavities, which are resonant at 440 megahertz. So as the beam goes by, you inject the wave, and the beam stops being laminar and starts being bunched. And then you're amplifying. You're pulling power out of the power supply and amplifying the wave, 4 cavities, and then you extract it off here in a waveguide, send the signal out, the rest of the electrons crash into the collector plate and come back. Unfortunately, to get the acceleration you want to, you have to put 90 kilovolts negative down here and ground the top. But you're trying to generate 1.25 megawatts per tube right in place. So this is an example of doing all your power in one place. Unfortunately, the Freescale people are not at this power level, for example. Somebody mentioned Freescale a little earlier. This is the on-off switch. This is our modulator deck, which has to switch 120 kilovolts at 4 amps maximum. And there's a hospital X-ray tube for on and a hospital X-ray tube for off. So these are big switches, essentially. And you notice it's dripping. That's because air breaks down at 7 kilovolts per inch, so if you leave it out in the open, it'll lightning arc to anywhere within a foot that's even close to ground, so we have to bury it in 5,000 gallons of dielectric oil to do all the bus connections to this cabinet, which has the Klystrons in it. So lots of care and feeding, which is why not a lot of people do this. This is our waveguide. This is the 440 megahertz waveguide I use. L-band and S-band for comparison. This is WR2100 waveguide. It honestly looks like HVAC duct. It's about yay big. Very thick walled for low loss. And we have about 1,500 feet of, well, maybe 1,200 feet of runs like this, all surplus. And just in case you think I wasn't telling the truth, there's a ruler that's 21 inches wide or 53 centimeters. And you all remember your TE10 mode cutoff frequency, don't you, for rectangular waveguides? So the bottom cutoff is 281 megahertz, and the top is 562, and I use it at 440, so I'm right in the middle of the transmission frequency path. And it's got very, very low loss. I don't remember the number, but if we switch back to English units, per 100 feet, it's in the 0.05 dB range, or somewhere in that range, because you've got a lot of metal. This is a rotary switch. This is a rotary joint, rotating antenna transmitter on the ground. So this is fixed to the ground, and this is now rotating with the platform. And this is our fun cable wrap, which means I can't keep spinning in a circle because I pull all the cables out. This is rated actually far higher than this, but so for us, this just kind of lazes along. But this is another piece of gear. There's the antenna. I've mentioned that already. Dates from the early 1960s. Although it didn't arrive at our site until 1978. And that's the Zenith Antenna, looking up at the feed structure. This is what we use coming back because this is a really, really weak signal. So Angle Linear was a person that actually some people in the amateur community will recognize. We also used Advanced Receiver Research ARR preamps, which again, for people working at 70 centimeters might be familiar. This has got about 20 dB gain, and it's only got a 50 Kelvin noise temperature, and it's at room temperature. You don't have to cool it. Better technology is coming. Gallium nitride is going to do much better than that. We'll probably drop this noise temperature by a factor of 2. If you look in here, there's a couple of hybrids. There's an input transistor and an output input amplifier and an output amplifier and some conditioning. So that's what we use. That's a FEMT for those of you who like microwave devices. And the other thing that I will show you before I stop showing you the big research thing is that we need a TR switch. We're just sharing the same antenna for transmit and receive. You don't want to leave this thing hooked up if you're transmitting 2 megawatts out the antenna. We have occasionally done that because the control signals have failed and this all turns into charcoal and we have to replace it. It's a nice fuse. So how do you do that? That's our pin diode switch. So anybody use pin diodes here for switching? Pretty fast, right? You have to drive this one at 15 volts positive and then slam it at about 270 volts negative to keep to drain all the charge out of the junction when you want to. But this is what keeps the receivers happy when we're transmitting the pulse, and then we hook them back up. So research grade stuff, large, expensive, hard to maintain, but you can do a lot with Spaceweather. The systems that we all work with here, much more modest than this, have a lot of geospace information in them. So I don't want you to get the idea that you have to do this in order to do research. So I'm talking to you about the value of partnering between amateurs and professionals. My point is, as is many things, we've been here before. You just may not have been aware of it. Anybody know who this guy is? My hero, Edwin Armstrong. This is QST February 1920, when he was president of the Radio Club of America. Some of you in the New York area may know that. This is his patent drawing for the feedback super regenerative circuit, and I won't get into the argument about Lee DeForest and Edwin Armstrong and David Sarnoff, but you know which side I am on. But a new method for the reception of weak signals at short wavelengths. Starr, President of Radio Club of America. So where was this first published? 1920, folks. Sarnoff, you might know Armstrong, who liked to tick off people, and he also really liked heights. That's him. And here he is with no harness. He would climb up to the top of this. This is the WJZ transmitter in New York City, and he would put 1 foot underneath the strap and do one of these, and then have somebody take a picture of it when that would be left on Sarnoff's desk. Drove him crazy. So we have iconoclasts, not only some of the people in this room, but also even at people like Armstrong. This is QST from February 1922. This was a transatlantic experiment. And those of you who have good eyes, look at the call signs. 2FD, 2FP, 8XK. Before we had standardized anything, right? All CW people, and I love this caption, you know, very nice thing. ARL successful overseas listener, and what worries me is that's not plural. One successful listener overseas? I hope not. But there you go. See? There's always a person who knows much more history than I when I show stuff like this. But amateurs trying to figure out propagation back in the 20s when radio was hot, right? Everybody was building radios out of, you know, breadboards, actual breadboards. CQ. Late 1940s, early 1950s, at the point when VHF was the edge of the envelope for propagation. We didn't really know a lot about it. CQ actually coordinated stuff with the Air Force Geophysical Research Laboratory, which became AFRL. This thing ran for 3 years, 500 registered amateurs, 100,000 observations collected. People got certificates, and look at all the things that came out of it. Transequatorial propagation, VHF openings between the hemispheres, sporadic E. Back in the 50s. Here's an editorial from 1949. Look at the yellow. Observations are needed to fill many gaps in the theoretical basis of radio wave propagation. The number of observations needed is far greater than the facilities of even the well-organized government research establishments. You see why I'm making this point. Observations by amateurs when properly gathered, screened, and tabulated, which is something that we're going to be talking about tomorrow, the importance of documentation. You can make measurements as long as you record what you're doing, you can make a lot of stuff out of them. But here we are in 1949. There's a lot of modern examples, and I'm going to just go quickly through some of them just to show you that this is already happening today. This is my friend Jody Kovitch, K1YOW, who lives in Harvard, Massachusetts. He started this all on his own. He was just interested. He's a 6-meter fanatic. He loves sporadic E. And this is his shack, by the way, just to show you the level of equipment he's using. Real QSL cards, right? And here's his particular setup. He does a lot of FT8. We mentioned FT8. And one of the things he noticed is, that there were all of these links, for example, between the US and Europe, but nothing over here. And so this was sporadic E season in June 2016. The VF gods were smiling on us this day, right? Because we had reporting networks to check this out. And what Joe noticed was something that actually the professional research community has been thinking about for a while, which is right where all that was happening, there were tropospheric weather systems. So there were very intense lower atmospheric winds that were actually, we think, generating signatures in the upper atmosphere and creating shears that pile up ionization and make sporadic E layers. This is not surprising to the meteorologists or the upper atmosphere community when we mentioned it to them. But they didn't know about it. And Joe did this all on his own. It's just somebody being a keen observer. I am talking to a room full of keen observers here. And that is really important. We mentioned the eclipse, okay, which we had done a number of things. This is my dad, who I set up with a Panasonic shortwave receiver, and I said, Dad, listen to WWV every 10 minutes, write down what the S meter does, and listen to it at 10 megahertz and 15 megahertz. This is a plot of what he heard as a function of the eclipse. As the totality passed between him and WWV, the S meter on the radio went down and at 15 megahertz and 10 went up. In other words, it started to turn into night. It's asymmetric. And then it came back. Notice the sophistication. Yes, he's writing that with a pencil. My dad will turn 90 in November. He had never done anything like this before. He was totally thrilled to participate. I gave this data to our friend Carl Lewitschwab, K9LA. Yep, he ran Prop Lab. There's Dad. This is 10 megahertz. The hop got to him before the eclipse, and there's 15. The hop missed him at 10 and got to him at 15 before the eclipse shadow went. It goes reasonably well. And don't ask me how poorly the Panasonic S meter is calibrated. I think I worked out 1.5 dB per S unit. Anybody know that it's supposed to be 6? But it was enough for him to do that. I put a correction in on this plot, okay? So don't worry. This doesn't just go to upper atmospheric stuff with radio. I mentioned this to somebody yesterday, I think, at dinner, and they kind of were a little incredulous. This is a project called AuroraSO, which is run by a scientist named Liz McDonald, who's now at Goddard. They literally try to identify where the aurora is by collecting tweets that have the word aurora in them. This is a website that I grabbed. This is their snapshot this morning. You notice that it says positive sighting, negative sighting, unverified tweet. Verified tweet, you could become a verified observer by submitting things that get checked. And they vacuumed this up, and everybody said, there's just absolutely no noise, because, you know, somebody whose daughter is named Aurora, who says, look at Aurora, you know, and tweets that, is going to fall in the filters. I'm going to show you a movie right now. This is a model of the auroral edge using Ovation Prime, which is a space weather real-time operational model, and you're going to see dots here. The yellow, basically positive sightings are green dots, verified reports of things like somebody saw aurora some direction are blue, negative are red, and you can watch. This was in a storm in March 2015, and you'll notice that at some points, suddenly things start to light up. Oh, see some people starting to see stuff. And then as the aurora came along, watch, boom. People are using this now to determine the auroral boundary, because there's a lot of people out there who really like to look at the aurora. The article is Citizen Scientists Help NASA Researchers Understand Auroras, so you can do this. And then, anybody hear of Steve? This actually hit some of the thing. This is something called, it turns out that auroral photographers for decades have seen this really funny purplish sort of diffuse emission. The high latitude aurora is up here. This is definitely subauroral. There's no particle precipitation happening here that we know creates the aurora. What the heck? This picture is from the Alberta aurora chasers who drive around in trucks, you know, and look for aurora. The science community only got engaged in this 2 years ago, in 2016. We don't know what it is, but it is not aurora. Here's a paper. And it turns out if you read the abstract, we think this is a new phenomena that is not connected to the normal things that run the aurora. It's either particle precipitation at an energy range we did not know about, or it is something going on internally in the atmosphere. But the amateurs have known about it for decades. We just didn't connect the pieces. Anybody been around when a solar flare happens? It's not the most pleasant job in the world. When you get a very large solar flare that comes off the surface of the sun, you get prompt ionization deep down into the D region. And what you actually get is wherever that's where the noon is, you get wipe out, this is 30 dB of absorption at 7 megahertz. This will just completely destroy the bands. This was a double flare that occurred on September 6th of last year. The second flare hasn't happened yet. We're waiting a little bit here. There's the second one. Everywhere in the sunlit hemisphere, you're going to get not much for quite a while if you're trying to use your radio. This is Jose Nunez, who is, at the time, was at Portugal and was operating in the CQWW Worldwide CW contest when a flare went off in 2000. I'm going to play for you what his radio sounded like. Things are going along okay. You hear the noise background coming up? Gone. And this is a contest. People were screaming away. You couldn't hear very much. And then what will happen is he goes nuts because he figures that something's wrong with his antenna or his radio. So he just starts tuning all over the place. There, pop. He'll turn up the volume in a minute. What the heck is happening here? Where's all the CW signals? That lasted for about 4 or 5 minutes. So there's scientific data in that too, if you can collect it. You can do polarization studies. This is our friend Ben Vitfleet, who is in the UK. He's actually, his day job is with Netherlands Radio, and he's also a student at the University of Bath. He developed a turnstile antenna to look at left-hand and right-hand circularly polarized radiation for NVIS. So he's trying to do emergency communications and look at what is most efficient for NVIS communications out to maybe 500 kilometers. And what he found out was that if you look at the ratio between the left and right polarization coming into his antennas, there was something called happy hour. At sunset and sunrise, there was a point where the ordinary waves were going right through the ionosphere, but the extraordinary waves were being refracted. So it was suddenly polarized for a little while. He's using this to try to improve the reliability of NVIS communications. He's an amateur. He's doing this just because he's curious. Citizen science. And this is Radio Jove. Somebody mentioned Radio Jove a little bit earlier. This is if you want to build your own radio telescope and listen to decametric emissions from Jupiter, you can do that. More citizen science. Or the Io Plasma Taurus, which has lots of stuff trapped in that magnetic field, which is screaming away. So, there are a few natural phenomena that we can see that I think we can study with not only the professional networks, but with crowdsourced stuff. There are lots of signals we can use for geospatial research which are free to you. You don't have to pay for the transmitters. This is from 70 megahertz all the way up to L-band. All of this forest of stuff are various digital television transmitters, some radars. The GPS cluster, of course, is up here. All of those can be harvested as a forward scatter thing to act if you capture the right bandwidths to do basically refractive or in some cases scintillation or scattering work without having to buy a transmitter. The universe is filled with things that emit radio waves. You could do radio astronomy, for example, from stuff from this is the radio Milky Way. This is what the sky looks like in radio at 408 megahertz. Planetary radio emissions, we mentioned Jupiter. The sun screams away at VHF to UHF. Sometimes solar flares have these bursts that descend. All of that can be seen in radio. That's just to show I/O here again, as Bob has already mentioned. There are huge structures in electron density that actually occur right over the continental United States that weren't honestly understood until some people at MIT, including my colleague John Foster, started working with them in the early 1990s. That's the continental US. That's an electron density gradient. Look at this. Sharp gradients bend HF signals. Imagine what signals trying to go from here to there do when they hit a wall. They go whoop. So there are signatures of all of this geospace coupling in the point-to-point propagation. Nathaniel already showed you some of that. And the ionosphere is fluctuating. And that actually has direct effects. These are called traveling ionospheric disturbances. These are wiggles, okay, that propagate just like waves from their sources. And look at their periods, 15 to 60 minutes, velocities of a few hundred meters per second, wavelengths of several hundred kilometers. They're going to get in the way of some of your propagation paths. And Nathaniel correctly points out that sometimes when you guys hear fading, this is probably related to it. They look like that. They are really a type of HFQSB. So it's an annoyance for you, but it's a science signal. Because you have fluctuations in the atmosphere, they're changing the refraction paths. There are many things that generate traveling ionospheric disturbances. This is a geomagnetic storm, where I take off the background and I look at the residuals from a high latitude source. That's the Aurora launching these waves. This is the eclipse I mentioned to you yesterday. That is a Falcon Heavy launch from Vandenberg Air Force Base, or nearby. That's SpaceX. And that happened just this summer. Look at the wave launched. You should see the plots. They're not as pretty from the Apollo Saturn V launches. Quite spectacular. All of that generates ionospheric disturbances, and we still don't know we don't know quite as well as we want to which wavelengths are preferred. Those of you who like DSP, there's a giant filter in the upper atmosphere. What's the filter coefficients like? We can find out. And so Nathaniel's going to talk about, he did his thesis, in fact, on refractions that were happening at HF frequencies. So if we build something that can measure these refractions in a way that's a little more calibrated than just a random point-to-point link, we can actually do fundamental traveling ionospheric disturbance research. And I think that is something this community can really help us with, and I think we'll be talking about that tomorrow. But this is happening at HF, right, where we all live. Finally, I want to just think about a couple of guiding principles here. It doesn't matter amateur or professional, this is just an approach, okay, that may help put some thoughts in your mind about how we might actually design something that would be easy to deploy, reasonably low effort, but that would start generating some of these signals. I don't know if you've ever seen this quote, but you know, the whole idea of correlation analysis is if you know what you're looking for, it's easier to find. You're quantifying the known, all right, which is interesting in some respects, but I like discovery. That's funny. Why did that thing show up? Sometimes it's harder to conduct professional studies with here as opposed to here, because people like you to quantify what's already known because it's easier to fund. But this community likes discovery, so you guys are a perfect partner for this. Is it science or is it communications when you're dealing with a radio signal? Well, the traditional paradigm is that you have some kind of RF transducer here with a stable oscillator, and you take some data and you're over in communications, so latency is absolutely critical. And I've heard talk after talk here worry about, oh, the board has to be fast enough so that we don't drop signals, because what are we doing? We're trying to run a communications channel, and if we drop information, a lot of the algorithms are reasonably brittle to that. So you take the RF transducer, maybe these days you run it through a ring buffer, where you buffer some of that, and then you do some kind of information extraction, the traditional tuning, you tune to the band you want, you demodulate, and then you produce a communications product. Well, here on science, the difference between a lot of the science analysis and a lot of the communications is that latency is much less important for us because we can record it and go back and analyze. We don't have that real-time, gotta do it now kind of thing. And I reanalyze RF data that I took decades ago. I have voltages, raw RF voltages at about 100 kilohertz outside my office that we took in 1999. Why do I need to deal with them? Because if I'm making a long-term trends measurement and somebody wants me to go back and reanalyze it, they might want that. They might want a 50-year trend. So we typically reanalyze RF data from decades ago, and we do it by a similar pipeline. We might need a stable clock because we might need to tag our data with universal time. But we run it into storage. We store it and then we pay it out using things like multicast. Phil has talked a lot about multicast. We can attach multiple clients. We can generate science products. We can go, what the heck was that? Well, rewind the tape, go back and look. We can do both if we think about it beforehand. There's no difference in this architecture. There's just the real-time thing and then the thing where I can record it and do it later. Ring buffers are great. They're wonderful. Whoops. And the ring buffer didn't like me because it said, oh. We've been doing this in software radio for a long time. Bob, I apologize because this says Joe Matola, and I know you were there along with a lot of other people. It's just that sometimes the heroes don't always get the publications.
He and I started the business together.
There you go. Oh, I'm sure you do. Software radio was being done, of course, in the 70s for, not open systems. It starts to emerge in the 80s and into the early 90s, but of course it was being done in ASICs because processors, that's what you need to do. We've been running a software radar since 1994. When I first got to Haystack, this was something that I actually dealt with. And if you looked at the architectures, they were more complicated than just running a direct sampler because you had to go through more, crunch the information down before you could deal with it. But it was a software radio, and then we could store it and run the clock back. Modern software radios, we have this wonderful deal, right? We have Gigasample per second radios are now showing up. We've got the low-cost dongle things, which have limitations. We have medium things. You've mentioned Matt Edis. Many times we use a USRP as a production, in our production system now. There's the Pitaya. There's a Xilinx board to chew some data. The radio cost is all over the place, but the radios are not the important part. It's how you store and interpret the information that's the important part. Because we have discovered you're always going to be changing your radio out at some point. But the procedure that you use to deal with the data to calibrate it does not change. That's the application stack. It's all about software patterns, voltage level data patterns. Grab the IQ samples, record them on disk, buffered. Deal with pipelines that then gradually add metadata to that stream. The A to D samples don't mean anything unless you tell me what frequency they were tuned to, what their bandwidth was, what antenna were they hooked up with, and gradually you attach metadata to this until finally you have a product that you can actually use for a scientific thing. Somebody else wants to do something different metadata path. And as long as you think about the software flow beforehand, you can make more than one thing happen from the software pile. We drew this picture in 1996. And this is the architecture for our software radar. So I can tell you we've had more than 20 years of experience. It works wonderfully well. I use agents that I wrote in 1998 that I have never changed because we did the architecture right from the start. And we've changed out radios. This is the W, by the way, is workstation. We actually moved, we deal with bandwidths that are like a megahertz to maybe 100 kilohertz. We moved to general purpose computing a long time ago because people time is expensive and we try to optimize last. But remember, we don't have that latency problem to worry about most times. If we can record it, we can deal with it. We have a very nice container for raw voltages that we're trying to promote, and we've actually open sourced it. This is essentially an HDF5 based RF format for raw data recording. Some of you may know that the manufacturers, of course, have created their own raw data formats, but a lot of them are proprietary and they're designed for instrument to instrument. The thing about this one is that the software interface to actually get at the data is open the thing, figure out the absolute time in UT that you want the sample, multiply by the sample rate, and say, give me a block at that time, and the software takes care of the rest of it. And how many times have you all written buffer code? Where's the sample I want? I've got to count 5 files forward. All right, I got to go 100 samples in. I've written my last bunch of that code. I don't want to do it. The nice thing about this is that it's open source. We have a ring buffer-based recorder available as an example, and if you don't want to use the toolkit, you can read the HDF5 files directly, and they're documented. So it survives the future. I encourage you to take a look at this. We spent a lot of time working with it. The real thing is that it's order 1 lookup. You can randomly wind around in time, because we like to do things that are back and forth in time because we have the recordings. This is a tool that's available. We don't have to create things that look like what we've done before. This is a wonderful beast. How many has ICOM sold? It's a 7300. I don't know. It's a lot, and it's familiar, and it looks like a radio. How old is TiVo now? It's been around for a while, right? That's a picture of live TV. You can press live TV and rewind it backwards. Why can't we do that? We can. But it's not a familiar interface. It's not an or, it's an and. We should be able to do both of those things. This, by the way, is an Agilent. This is their signal surveyor. Notice the words 4D. That's in space and time. This is for the professional community. This is, if I sold my house, I'd probably be able to afford some of that. But it doesn't matter, okay? You guys are implementers. You are innovators. You can do this in a low cost. We can do this now. And I think TAPR is the perfect organization to do things that don't look like what you've already done before, which is in your DNA to do things that are not available, but that make intellectual sense. So I'm going to leave it there. I really like this quote. The best way to predict the future is to create it. I think the science community is ready. I think you as the amateur community are ready. I think TAPR itself is ready. We can get a lot of science out of this if we work together. And so watch the space, show up tomorrow if you can in the morning, help us discuss some more of the details of where we could start on this. So I'm going to thank all of my colleagues who really contributed some slides that I shamelessly stole. I really want to thank all of you for listening, and honestly, I'm honored to be among this level of innovator. I'm really, really pleased and privileged to have been given this, and I'll take any questions you've got. Thank you very, very much.
Okay.
Questions?
Go ahead, Mark.
There's been a lot of discussion in the press recently about the reversal of the magnetic field.
Yes. So he's referring to let us all bow our heads and mourn the loss of solar maximum. We are most definitely right in the pit, in the depths of solar minimum. My favorite web page that I will look at right in a moment here is the Spaceweather Prediction Center, which I will bring up, swpc.noaa.gov. And if you go there, you can go to the Space Weather Enthusiasts dashboard, and you can go down here, and there's a bunch of different things. And one of the things you find is that. Where are we? There. Straight in the depths of solar minimum. So what Mark is referring to is that there was a press release 2 or 3 weeks ago that somebody had found, some of you may know that sunspots reverse magnetic polarity between solar cycles. Someone had found a spot of the opposite polarity and said, it was great, we're beginning of the next solar cycle. Unfortunately, there's something called the butterfly diagram, which says that the new spots appear at high latitudes on the sun, not in the equatorial plane. The new spot was right at the equator. It turns out that 2 or 3% of the sunspots are the wrong polarity at any point in the cycle. Oh, yes, and he's also referring to another thing, which is that I referred to all of this magnetic field structure, right, that's structuring all this plasma, and that is obviously organized by the background magnetic field. And if anybody is following this, you might know that the magnetic pole is actually racing away from us. It has gone up through northern Canada. It's entering the Arctic Ocean right now. And there's a paper that predicts that in 50 years, the pole will be in northern Siberia. And we will be at a much lower magnetic latitude than we are now. So the dynamo is actually beginning to slow down at the planet's core. There have been periods in Earth's history where that's happened, where we've actually flipped over the pole. Maybe that's starting, but right now, I'm getting to be lower magnetic latitude every day because I can't push Millstone Hill. Right now, if I was in Goose Bay, Labrador, I'd be about at the magnetic coordinates that we were about 30 years ago. So it's moving fast. In fact, if you look at it, it's actually accelerating. It's kind of interesting. Yes, Scotty.
Can you comment on some people's opinions about the declining quality of our sunspot cycles the past couple of cycles? And it's something called the Modulator.
Right. So Scotty is referring to the fact that there is a progression of sunspots that if you looked at this, if you looked at this cycle right here, this is the sunspot number. This is the cycle we just went through, and that was the previous one, and the one before that was higher still. There are people there have been periods in the sun where everything has gone click, 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 click. Nobody knows for sure. The sun has many, many patterns, some of which are 100 years long. Almost every prediction I've seen of this stuff has turned out to be wrong. So don't give up hope yet, okay? Don't throw away your 15-meter Moxon or whatever it is. Keep it on the pole. It'll be useful. You can even see that, by the way, there's two things right here, even in this diagram, that will tell you why everybody is really bad at predicting this stuff. First of all, look at the last solar cycle. There are 2 peaks. See them? 1, 2. It wasn't single peaked. I remember getting to here, and people were like, oh, we've already, boy, talk about being wimpy. And then it went back up again. And it turned out that was because the sunspots in the northern hemisphere were getting to the equator a little faster than the ones in the southern hemisphere. That does happen on some cycles. The other thing I remember is this. Anybody suffer through the last solar cycle? It lasted 18 months longer than it normally does, so we had about almost a 13-year solar cycle. There were a lot of talks at conferences right here about what happens if the sun just shuts off. How long is it going to take for the disk just to spin down to nothing? Apparently it has happened before. And so people referring to the Maunder minimum, there's the Dalton minimum, there's a couple of other minimums back in history. I hope we're not there.
Do you have any clue as to why these minimums occurred?
There have been many, many theories about why sunspots appear in cycles the way they do. There's a theory about there being a conveyor belt, so that the spots are on the surface of the sun for one cycle and then they sink down and they ride the conveyor belt under the surface and then come back up again. That one got torn to shreds by this particular solar cycle. There's one that says that the problem is that the sun is a magnetized fluid, which is spinning at different rates at different latitudes, and the magnetic field is just absolutely 100% horrible. You asked. You never want to ask me that question. All right, I'm going to look up something called the Sun Today. All right, the Sun Today is run by, this is run by essentially Los Alamos people there. This is the sun now. Okay, current observations. This is the Solar Dynamics Observatory, which is out basically just looking at the disk, okay, and looking at it a bunch of, that's the wavelength, by the way, that's the wavelength in angstroms. So put a decimal point here, that's 17.1 nanometer wavelength. So this is the extreme ultraviolet sun. That is the thing that's ionizing the upper atmosphere. Notice it's not a featureless white disk, by the way. But what I want to show you here, notice they're doing it in a bunch of wavelengths. By the way, this is a 4K by 4K pixel image taken in 7 spectral wavelengths once every 7 seconds. And it is downlinked by a satellite which is dedicated to just looking at the telemetry channel and doing the downlink. They've been doing this for 7 or 8 years. Imagine how many images they have. You like big data? There you go. But what I'm going to show you is somewhere here we have the magnetogram, and one of these here has, see, it looks really pretty. One of them has an estimate of what the magnetic field looks like. So you can actually make a magnetogram, and that's one side of the magnetic field and that's the other one. There's a loop that comes up and down. This is not even close to being dipolar. It's chaotic and these things move around, and you should see what it looks like at solar maximum. And this is probably a couple of minutes ago. So notice it's not that featured because it's solar minimum. But if I can find the right thing right here, and notice that, see, there's the full resolution 4K image. They used to have a combined false color one, which I will attempt to find here, that had a map of the magnetic field, which is just utterly scary. Now they may have taken it down. In any case, you can note it, I mean, not at all a nice white disk with a few little spots. So the different wavelengths, by the way, are different solar altitudes. So some photons come from deeper within the corona and the photosphere, and some of them come from higher. So you look at it different wavelengths and you can build an altitude picture. Very dynamic. Other questions? Curiosities? I can't believe that you guys didn't say, where's the second dessert?
Well, there are door prizes.
There are door prizes.
Okay, thank you very much,
Thank you
Phil.
very much, folks.